Okay, so first we rewrite with rational exponents, right? That square root becomes parentheses to the 1/2. And then we can bring that 1/2 down in front because that's the power property. And then we can continue with quotient property, right? So all this time, there's no calculus involved here. We're just splitting up our problem so that our derivative can be an easier process. Okay, so natural log of A over B is equivalent to natural log of A minus natural log of B. And now we can apply our derivative rule. What's our derivative for natural log? What's our rule there? Natural log of U becomes what? Yeah, U prime over U. Yep. Apply that twice and any questions of one? Yeah.
Why would the -2 stay in the 12? Oh, because it'll just cancel.
Yeah, it just cancels out between -2 and +2. Yeah.
Would you take off the 5?
No, I wouldn't. Okay, let's look at number 2. Find dy dx for y is equal to x raised to the square root of x plus 3. What do you notice about this form here?
So x there's a square root
Mhm.
exponent and there's x.
Yeah. So do we have a rule for that? Well, what's the strategy for a problem like this? Yeah, we got to introduce natural log. So we talked about how there's 3 scenarios that kind of look similar to this, right? If it was x to the numeric value, then we do power rule. If it was 3 to the x, then we do exponentials, right? Something like number 10, right? This is a constant raised to a variable. We have a rule for this. But this one, variable raised to a variable, we're kind of stuck not having an explicit rule, but you can work around it by finding a way to bring that exponent down. So we can use log differentiation. So we'll involve natural logs. Let's go ahead and rewrite that. Radical as a rational exponent. Okay, what can we do next? Yeah, now that we're inside the natural log expression, we can bring that exponent down. Okay. So no calculus so far. All we've done is we just rewritten it into a form that is easier to manage than what we have started with. So now we can move on to our derivative, right? So left side, there's a little bit of what here? But what's the derivative of natural log of y? Yeah, so if it was just y by itself, then it would just be dy dx, right? But natural log, we have to involve natural log's derivative, which is u prime over u. And then we need to attach dy dx because we're doing implicit here. So yeah. And then the right side requires what? To find the derivative. Okay, it's part of it. Not implicit. We do implicit if you see y's involved, right? But there's no y's involved here. What else? How many terms do you see there? 2. And what's the operation between them? So we do what? Product rule, right? Do we see that? Hopefully, we've seen enough product rules to recognize the need for product rule, right? If I have two variable expressions being multiplied together and I'm asked to find the derivative, we got to go through product rule. Right? So let's step through product rule now. Okay, what's f prime here? So this one is a little bit of chain rule here. Outside times inside's derivative, right? What's outside's derivative? Parentheses to the -1/2. Keep the inside intact times what? What's inside's derivative? 1, right? So no impact, but technically it is still chain rule. And then the g function. Back to f. G prime. U prime over u. Okay, so we basically are at the derivative level. Now it's just to clean up, right? So the calculus is done. The calculus was only from here to here, and then now we're done with the calculus. So what's our next step? What are we going to solve for? dy dx. Okay, so what needs to move?
The 1 over 1.
Okay, so when it moves over to the right side, what does it look like? Yeah, dividing by a fraction is the same thing as multiplying by the reciprocal. Okay, but then if we write our answer in terms, let's see, dy dx equals. Let's just do a little bit of cleanup here. Numerator and denominator separated. And what's one final thing that we can do to represent our derivative? Okay, so how to replace the y with x? Yep. Okay, number 3 and 4 involves derivative of inverse at a point. So let me remind us of the steps that we did for those. Remember that we have a special relationship between a function and its inverse, not only at order pairs, but also at the slopes. So let's say there's an order pair a comma b on the original function. But then on the inverse side of things, there's an order pair b comma a, right? And then also through their points, there's going to be a specific relationship between their slopes, right? If this is 4, this will be 1/4. If this is 9, this will be 1/9. So we create this little chart here just to kind of help kind of help map out what we're trying to do. If we're trying to find the derivative of the inverse at a point, we know that that x value is the x value of your inverse function. but you also know that that x value is the what of the original function, is the y value. So we start off here, and then we try to figure out what can we use to fill out this chart here. And we kind of have to go back and figure out what that x value is. But once we find that x value, we can see the clear connection between those two functions. And then everything is going to be done on the f side of things. If I can find the slope of the f graph at A, then that's going to lead me to the slope of the inverse at B. Okay. It doesn't have to be f and g here. It could be anything, but if we start with the inverse, then we're going to work with the original. Okay, so this one feels a little bit backwards here, but number 3 is the same idea. F and G are inverses of each other. That's what that first line tells us. F and G. If I insert one into the other, I get X in return. That's going to be that asymptote that is dividing the two graphs, or the dividing line. So I want to find f prime of 2. So I know my end goal is here. I know that 2 is the x value of my f graph. So 2 must be the what of my g graph, y value. So we need something that will allow us to fit into here. So there's some extraneous information that we're not going to need, but what order pair will fit into this information, this chart that we've established? G of what equals 2? G of 7. So if G of 7 equals 2, then we know there's an order pair on the f graph that's 2, 7, right? So there's our order pair relationship there between f and g. So if I can find g prime of 7, then that slope will lead me to f prime of 2. What's g prime of 7? Then what's f prime of 2 going to be? What do you guys think? Yeah, it's the same sign. You just do the reciprocal. Okay, it's not opposite reciprocal. That's perpendicular lines. Okay, it's just the reciprocal. Oh yeah, whatever I'm looking for, I'm always going to put that there, and then I'm always starting here, and I'm working my way around. Yeah, so whatever is the unknown, that's always going to put. I'm almost putting that box. Okay, so number 4 is the same idea. It's just that we may have to do a little bit more work for this portions because it's not given to us. All right. So here I'm trying to find the derivative of my inverse at 13. I know 13 is the x value of my inverse, which means that 13 is the what of my f function, y value. So what's our next step? How do we progress using that information? Yeah, so we know what the y value is for this function. We just don't know what the x value is. So we'll put 13 into the y slot. And then we're just trying to do a little bit of guess and check here to figure out our x value. Okay, so let me bring everything over to one side. Okay, so we said that we can find this number relatively easily. It's going to be a number close to 0. It's going to be a nice integer value. So we can start with 0. If 0 doesn't work, then we'll try 1. If 1 doesn't work, then we'll try -1, then so on and so forth. Right. So think about what numbers that we can test and what x value could work for this equation. 2. All right, so let's try 2 here. 2 cubed is 8. 2 times 2 squared is 2 times 4 is 8. So I have 8 plus 8 is 16. 16 minus 16 is 0. So 2 works. So if I know my order pair is 2 is going to work, I know there on the inverse side there must be an order pair 13 too. I really don't need this information. I just like to see that that relationally my order pairs will show that relationship. And now if I can find f prime of 2, then the slope on the f graph will lead me to the slope of the inverse at 13. Okay, so how can I work towards finding f prime of 2? Find the derivative of f of x. Okay, what's the derivative? Let's find the slope of the f graph at 2. Which is what? Three times 4 plus 8. What's that equal to? 20. So if the f graph at 2 is 20, then the inverse at 13 must be 1 over 20. Any question with this process?
Always look for the bottom right one.
Yeah. Whatever the unknown is, I'm always going to put in the bottom right corner, and then I'm going to work around my box. By the time I work my way around, I should be able to have enough information to get to my answer. Okay. Number 5 should feel like number 1. What can we do with number 5 here to begin with? Expand. Okay. So spend your efforts to see if you can rewrite the expression, clean everything up so that you're only dealing with a relatively manageable u prime over u. Okay, keep expanding, right? Those exponent, the first one can come down. We don't want to play the 2x cubed is, we don't have to adjust that. That's this is not a messy enough problem to, it's not worth the effort to expand this. That's already an easy derivative. This one we do want to try to bring the exponent down. Okay, any questions with 5? What can we do with number 6? Jump into product workout. F prime G plus F G prime. Okay, F prime G plus F G prime. What's the rule for e to the u? The u's of G prime, right? The original function times exponent's derivative. Yeah. So e to 5x squared plus 3x. Remember, your derivative will copy the original function first, and then the exponent's derivative, right? So your exponential function e will have the derivative that looks all like exactly like the original function. Okay, number 7. So I know that this is log base 8. This looks more intimidating because it feels like it's going to be a more difficult process than logs of other bases. But we're going to pretend like we're working with what? Pretend you're working with the log base 8. What base have you been working with that feels easier? Not base 10. Yeah, natural log, right? Pretend this is natural log. So pretend this was 2 natural log square root of x minus e to the x. How would you approach this problem if it wasn't log base 8, it was natural log? Okay.
Would it be 1
Um,
over?
yes, right. You're right. That's eventually the derivative. But if this were just natural log to begin with, how would you begin the problem? Sorry? Yeah, expand, right? So what would you do first? How would you expand it? That square root can be written as, then what would you do? Yeah, bring that down, right? The 2 1/2 goes away. So that's about as cleaned up as we can make it. We can't distribute that log base 8 through. What's the rule for natural log? Let's not even think about log base 8. What's the rule for natural log? Derivative rule. U prime over U, right? So log base 8 is also going to have U prime over U. So I don't want us to think that, oh, this is a brand new rule I got to memorize. It's basically just natural log, but there's something in front. What's in front of that U prime over U? Yeah, it's 1 over natural log of A. Because your derivative has a denominator portion, hopefully that will help you remember that your natural log of A goes in the denominator. So now we've gotten past the adjustments. Now U prime over U is what? What's the derivative of that parentheses? X becomes 1. E to the X becomes times 1. That E to the X times 1, right? E to the U times U prime. So no changes. All over.
Explains.
E to the X, right? Okay.
That's your answer.
Yeah. Okay, number 8. I mean, we obviously see a couple of rules here, but what's the big rule that we have to make sure we include here? Product rule, yeah. So as a reminder, this is, what type of function is this? Exponential, right? So base A, right? So the derivative for base A is A to the U times U prime, just like E to the U, but with a little bit extra in front. Right, so when we see A to the U, I want us to think in terms of E to the U, right? How would you do derivative for E to the U? It's the exact same process with just a little bit of conversion that's happened in front. Okay, so how do we do the derivative for 2 to the 3x? How would we start it? Times 3. Yeah. The G and F, I can just copy down from above, no changes. Okay, now G prime, very much like how we did log base 8 here. What's the base that's hiding here? 10. So what's the first thing that shows up? 1 over natural log of 10. And then U prime over U, right? Okay. So we take the derivative of what's inside the parentheses. 2 becomes, what's square root of x? It's x to the 1/2, right? What's the derivative of x to the 1/2? Just make sure we keep that negative in front. Okay, so I move things around here. I just push that x to the negative 1/2 down to the denominator. Also, I push this 2 down to the denominator as well. Okay, so number 9, how would you start number 9? Expand it, yep. Log base 2, pretend like you're working with natural log of u, still u prime over u. A little bit of coefficients conversion has happened in front. So. Okay. What rule do we use for number 10? What category is this function falling into? Exponential, right? So natural log of a times a to the u times u prime. So everything feels pretty straightforward, except what's messy about the u prime that we have to worry about here? We get to this exponent's derivative, what's involved? Same rule, yeah. So y prime is natural log of a times a to the u times u prime, and u prime is going to take a little longer to get through because outside's derivative times inside's derivative. Okay, just as a reminder, what's the derivative of 3e squared? 0, right? It's not 6e because e is not a variable. That's just a number. So that whole thing is just a constant, and constant goes 0. Okay, so 1 over natural log of a times a to the u times u prime. And u prime, we got to think about outside portion versus inside portion and take each derivative accordingly. What did you? Oh, sorry, my bad. This is wrong, right? It should be what? Just natural log of a, right? That is for. Sorry, that's my mistake.
Why do you put it in cube roots of wonder? This is times one.
Oh, this right here?
Oh, no, the 11, the exponent of the 11.
Oh, yeah, I could have. I just went back and forth. This one. I just copied down the exact original problem. Okay, number 11. We're asked to find the derivative. What is involved here? Implicit, because you see y is all over the place. Okay. What else? Is there anything that we can do before we do our derivative steps? Expand, right? So we prefer not to jump into u prime over u when this is in that fractional form, right? Let's make it easier. Let's do natural log of a minus natural log of b before we jump into our derivative step. Okay, good. So we want to expand. There's implicit, something else. Product rule, right? You see that x, y, that's product rule there. F prime g plus f g prime. Okay, but first let's expand, get the first terms to be a little cleaner to work with.
Can we bring the 5 down too?
We don't, not until you do the derivative, right? Now, we can do that if it was natural log of x to the fifth power, right? It was 2x to the fifth, there's no natural log. So if we bring that 5 down, then we're starting the derivative process. Okay, so everything is ready for our derivative steps. What's natural log of y's derivative? 1 over y. What else? dy dx, right? Oh, also, how many dy dx's should we be expecting when we do our derivative line? 3, right? Yeah. Okay. Okay, 1/2 natural log of x becomes just 1/2 x. F prime g plus f g prime. X is my f, g is my y. What does minus y turn into? Yeah, I like to put a 1 in front. Later, if we have to do any GCFs, it's nice to have that 1 there. So if we pull the GCF out, and we don't forget about that 1 that's still sitting there. Yeah. And don't forget the 3 is also getting impacted. That 3 will turn into a 0. Okay, so now, the calculus is done. Now we're just trying to group all the UIDXs together, factor the UIDX out.
Um. Can you put the two X at the denominator or,
Oh, put this 2x down here.
yeah,
We can't, you know why?
um,
Or can we not bring that 2x down here? Now, if it was this,
addition.
it's yeah. Anytime you have a connection to addition or subtraction, you're stuck. It's unless you do it, you know, common denominator, and do some additional work, you're not able to just bring it down, yeah. Okay, one final thing I want us to do, go to the very back page. See if we can do a quick practice, see if we can recall our derivative rules. Spend a minute doing that. So we at least have that daily practice of reviewing the new rules that we're going to be responsible for. Remember, these two are the major ones. If you can build 1 and 2, then 3 and 4, it's just kind of adding to the ones above it. Okay, what's natural log of u? U prime over u. What's e to the u? Log base a of u looks a lot like this. Right? You're still gonna have that u prime over u, but there's something extra here. 1 over ln log of a. A to the u looks a lot like this, the original function of the exponent's derivative, but with a in front. Right, the original function times exponent's derivative. Okay, come get your phones. We'll have another review sheet for you Wednesday. We'll work through Wednesday, Thursday, quiz on Friday.
Where the tangent line equations on, we just like find like the point and slope.
That's right. Yeah, and we'll finish that on Tuesday. Yep.
Can we work tomorrow for the remote thing? Oh. You ready? I did.
This way. I thought that thing is one. That's the fact that requires that you are.
Yes. But to make sure he's not another job.
So we just got another time.
I don't know.